Hey everybody, this is Mr. Piercy, and what we're going to be looking at in today's video is one of the three basic trig functions known as tangent. Uh, Now this is the first trig video that I'm making for this material, so let's just have a quick synopsis, if I could speak, of what the trig ratios are. Now there's actually 6 basic trig ratios, but let's go ahead and write out what they are. This one, even though this is the first video that I'm making, this is actually usually the third one that we talk about. We have sine, we have cosine, and then usually we talk about tangent. Now those are the 3 basic ones. The other ones that we have are cosecant, secant, and cotangent. Now in high school geometry, typically we only look at the first 3, sine, cosine, and tangent, because cosecant, secant, and cotangent, those are the reciprocals. So we'd say like CSC to abbreviate cosecant, and that would be 1 over sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Okay, high school geometry usually doesn't get into cosecant, secant, and cotangent. However, since we are talking about trig ratios, I think it's important to get all of the information out that we can. But speaking about sine, cosine, and tangent, what are those? There is a ratio that we use for each one. Sine is equal to the opposite side over the hypotenuse of a triangle. Cosine is equal to the adjacent side of an angle over the hypotenuse of a right triangle, and tangent is equal to the opposite side of an angle to the adjacent side of an angle. And there's a little acronym that we use to help us remember what those ratios are. It's SO, CA, TOA, where we look at the first letter in each of the 3 groupings represents sine, cosine, and tangent. And then the middle letter represents the numerator, and and the third letter, the letter on the right, represents the denominator. So that just kind of helps you remember how you set up your trig ratios. But oh, hey, look, I got an email. Awesome. So here, the definition of the trig ratio is the length of 2 sides of a right triangle, specifically the adjacent side and the opposite side of the right triangles. Now, how do we make sure that we can identify the things correctly? How can we identify what side is the adjacent side, what side is the opposite side of a right triangle? It has to do with where the angle is located. So here in the box that you're looking at here, it says we're looking at what is the ratio for tangent of A. Well, tangent is opposite over adjacent, so here, this is where we're looking. That's the angle. So the side opposite of it is side BC, but the side adjacent to it is the side that actually makes it up, which would be side BA. Well, some of you may be asking, well, why isn't the hypotenuse considered adjacent? Well, the hypotenuse is a specific side of the triangle. It is the side opposite of the right angle and is always the longest side of the right triangle. So because of its uniqueness, the hypotenuse is always going to be classified as just the hypotenuse. However, the legs, depending on where the angle is, can be either opposite or adjacent to one of the acute angles. So just for example, what if instead we wanted to say, oh, what is tangent of C. Well, C, we relocate ourselves to this corner here, so the side opposite of it would be side AB, and the side adjacent to it would be side BC. So I would say the opposite side is AB over BC. So the ratio that we use for any of our trig functions, sine, cosine, or tangent, depends on which of the acute angles that we use, because opposite and adjacent change depending on their relative locations in the triangle. Now, you saw me on the last slide, you saw me use this symbol here, which you're seeing down here. That is the Greek's or that's the symbol for the Greek word theta. Just like pi is, all this thing here is, this is just a whole bunch of Greek letters, okay? There's several Greek letters that are used to represent an angle in when we're doing trigonometry. Theta is the most common. That's the most, the one that's used most often. The other ones that are that typically show up the one most regularly, if I could get it out, are the ones that I've highlighted. Alpha, beta, and gamma are ones that are also typically used pretty much just to represent angles when we're working with right triangles with trigonometry. But theta, that kind of circle with the line through it, that's most commonly used to represent the angle. Now here, this first skill that it's asking you to do is just says, can you actually identify the correct ratios depending on where the angle is located? Okay, so every triangle, every right triangle, I should say, has two acute angles. The two acute angles are always going to be the angles that we refer to when we're doing trigonometry. The right angle, the 90-degree angle, is never going to be our angle of reference, or theta. It's always going to be one of the two acute angles. So looking here, we're looking what's the ratio for tangent for S? Well, in this case, S is here, so the side opposite of it is side TR, and the side adjacent to it is side ST. So we can take that information and just kind of substitute it and let the calculator simplify the values for us. Now, one of the things that we get into in more like pre-calculus or a separate trigonometry class, one of the things that you'll look at is the domain trig ratio. And tangent is the only function, the only trig function that actually has a domain that's greater than 1. Sine and cosine never have a domain greater than 1. So sometimes if you have a fraction when you're doing sine or cosine, and you see, oh, hey, that's going to give me a fraction that's greater than 1, you can recognize that you probably made a mistake somewhere. Oops, let me erase that. And so the next one, what we're doing is we're moving on to looking at the angle from R. So here's my angle of reference. So the angle, or the side opposite of that, is side ST. The side adjacent to it is RT. And so that's how we set up our ratios. And typically we write it out to 4 decimal places. Now, if you did this on the calculator, if you said 5 divided by 12, it certainly doesn't stop at 4 decimal places. This is just where math has decided this is how far we should round out when we're doing these trig ratios. Now, way back when, before everybody had calculators readily available, when all of this math was being developed, people didn't have the calculators. They had to develop a trig table. And so they decided, well, we're going to just carry it out to 4 decimal places for accuracy purposes and stop there. And they would create like a huge table for all of the possible ratios for sine, cosine, tangent, cosecant, secant, and cotangent. Okay, well, since we have a calculator available, stopping here, actually making this number and then doing math with it, we're really not going to use that number anymore. We're actually going to use the ratio itself, whatever it happens to be, and let the calculator kind of do the work for us. So here at this point, go ahead and pause the video, or rather answer this question here. Pause the video, see what you come up with, and then when you have your answers, hit play again and see, did you get this correct tangent ratios based on what I've shown you so far and then I'll show you what my answers are. Alright, hopefully you pause the video and you've done the practice problem yourself and see what we have. So we have two ratios for tangent that we could have, one from angle B and one from angle C. So here's the ratio that we get for angle B. Again, opposite over adjacent, AC over AB, simplifies to be about 3.4. Then we're going to go to tangent for C, which again is opposite over adjacent, AB over AC, which simplifies to be about 0.3. Okay. Now again, the numbers, those 4 decimal place numbers, we're really not going to use those too much. We'll actually use the fractions, whatever those give us. We'll type that into our calculator when we do our work. So here, now that we know how to actually find the ratios for tangent, opposite over adjacent, how are we going to use that to find the missing side of a right triangle? So in the example that we have here, we have a right triangle where one leg is 17 units long, one leg we don't know, so we call it x, and one of the acute angles is 31 degrees. So that 31 degree angle is our angle of reference. So in this case, theta, gamma, whatever we use, theta in this case is our 31 degrees. Typically we write it off as we'll start it off as saying tangent of theta is equal to the opposite side over the adjacent side. And then we just substitute our numbers. So in this case, I would say tangent of 31, which is where they're kind of starting it off here. Now we can just substitute our opposite side and our adjacent side, and in this case, the opposite side of the angle is 17, and the adjacent side of the angle is whatever side x happens to be. At this point, it's just an algebra problem. We have tangent of 31 is equal to 17 divided by x. Since x is in the bottom of the fraction, we multiply both sides by x to get it out of the denominator. And we wind up with x times the tangent of 31. Well, now we have to get x by itself. We've gotten it out of the denominator, so now we have to get x by itself. So now, since tangent of 31 is multiplied to x, we moved it to the other side of the equal sign through division, and we wind up with x divided by tangent of 31. Now this is where way back in the day we would have to refer to a trig table and see what does tangent of 31 simplify to be? What is that decimal number? And then we would say 17 divided by whatever that decimal number is. Well, since we have calculators, we're not going to use that decimal number. On the calculator, you're just going to say 17 divided by tangent of 31. Now real quick, I'm sorry to make this longer than necessary, but on your calculator at this point, before you actually type anything in, somewhere on your calculator there's probably something that looks like this: degrees, radians, and gradians. So degree stands for degree. This is a radian, and this is a gradient. Now this one I've never used, ever. But degrees, we know what degrees are. That's an angle measurement. Radians are also an angle measurement. It's just a different way of measuring it. Just like I can measure a line in inches or centimeters, I can measure an angle in radians or degrees. The quick definition of what a radian is if I have a circle with radius r, if I take whatever that radius happens to be and I lay it out along the circumference, where this arc length here, if this is r and this is r, this angle here is 1 radian. Okay? On your calculator, most calculators are set up to have the default, most calculators are set up to default in radians. Okay? And radians are not something that we typically use in high school geometry because most of our angle measurements are pretty much always going to be in degrees. Pre-calculus, trigonometry, calculus, a lot of the angle measurements that they use are in radians. So you need to make sure that your calculator is set to degrees at this point before you type in tangent or 17 divided by tangent of 31, because one will give you the answer in degrees, one will give you your answer in radians. So if you're not sure, ask somebody, come ask me, and I can show you how to do that. But 17 divided by the tangent of 31, when you type that into your calculator, you should get about 28.3 degrees. Okay, but we carried out obviously to 3 decimal places because, pre-AP math and AP math, that's the expectation, 3 decimal places. So here's just another example. Now we're going to use the tangent ratio again to find a missing side of a triangle. However, in this case, instead of looking for the adjacent side of the triangle, now we're looking for the opposite side of the triangle. So we're still using tangent, which is opposite over adjacent. In this case, the angle of reference is 62 degrees, so I substitute that in for theta. So I get tangent of, actually this probably should have said tangent of theta is equal to the opposite over adjacent and then substitute the 62, but either way, we wind up with tangent of 62 is equal to the hypotenuse over 100 because 100 is the adjacent side. Again, just like in the last example, the 100 is in the denominator of a fraction, and we have to get rid of it from the right side of the equation. So because it's in the bottom part of the fraction, we multiply both sides by 100, and I get 100 multiplied by the tangent of 62. And again, as long as your calculator is in degrees, you can just type 100 multiplied by tangent 62 and hit enter on your calculator, and you get about 188 feet for the height of the figure. Okay. Moving on, now we're going to take a look at how we can use special right triangles to find the tangent of a 30-degree angle. Now here we have a 30, 60, 90 special right triangle. So at this point we're going to say that the square root of 3 is going to be the side opposite of the angle that we're looking for, and the long leg is going to equal the long leg. Now we can use our rules for 30, 60, 90 triangles to justify what this is going to be, and exactly that's how it's set up. Remember, the rule for 30, 60, 90 triangles, one of them is that the long leg is equal to the short leg multiplied by the square root of 3. So the long leg is x, the short leg is the square root of 3, and we're going to multiply it by the square root of 3 from the rule, and that simplifies to be the number 3. Okay? Now will we get the same thing when we substitute our values? So here, the tangent of 30 is going to equal the opposite side over the adjacent side. In this case, that will give you radical 3 over 3. Now, at this point, you have to, you can type that into your calculator in radical 3 over 3, and that approximates to be 0.5774. Now, again, the decimal number, not really going to be used too much. We're going to stick with the radical version, the exact version, and because that's going to be something that will be used in future math classes when we build something called the unit circle. So here, I believe this is pretty much toward the end of our lesson here, so go ahead and answer the next 3 questions on your own, and when you're done, hit play again on your video player and see how my answers look compared to yours. Okay guys, so hopefully we have some good answers here. Here in exercise 2 and 3, find the value of the missing side of the triangle. So in this case, I think I have my work. There we go, somewhere over here. Tangent of 63 is equal to opposite over adjacent. And really, when I started off, that should really just be theta. That was my mistake. So tangent of theta is equal to opposite over adjacent. Substitute, solve for x, and we get about 6.6. On the other side, number 3, solving for the missing side here gives us about 35. And here, in example 4, suppose the length of the shorter leg was 1 instead of 3. So I'm just including the diagram here. I stole it from the previous example, but obviously now the short leg is going to be 1. Still show that it's going to equal to the same ratio. So here we have radical 3, or we have the rule for a 30, 60, 90 triangle. Sorry, I had a mental moment there for a second. And so we're going to just plug in our number. We say 1 for the short leg, and we get radical 3 for the length of the long leg. Well, now I'm going to take those numbers and I'm going to say opposite over adjacent 1 over radical 3. We have to rationalize it, and we still wind up with radical 3 over 3. So I know I gave you a whole lot of information here because typically tangent is actually the third trig ratio that we introduce. However, the curriculum that we're looking at here uses it first. Remember, SOHCAHTOA is something that we're going to need, but in this case, tangent, you need to understand it's the opposite side versus the adjacent side of a right triangle. The opposite and adjacent sides have to be the legs. Hypotenuse can never be opposite or adjacent to an angle, and the 90-degree angle can never be our reference angle, our theta. And the last thing is, when we're doing this stuff on our calculator, make sure your calculator is set to degrees and not radians. But that's it for this lesson, ladies and gentlemen. If you have any questions about anything you saw, by all means let me know and I'll help you out. Until next time, thanks for watching and take care.